In part 3 of section 8, we're going to begin looking at the process for solving a system. Now that we know a linear system either has one solution, no solution, or infinitely many solutions, we still need to know how do we figure out what the solution or solutions are. If there's no solution, there's really nothing to do, but if there is a solution, it would be nice to know where it's located. What is the ordered pair that actually makes this work? Or if there's infinitely many, what's the pattern? What do all the ordered pair look like that are going to be a solution to this system? So there's going to be 4 methods that we will look at throughout the course of this section and an upcoming section that will be acceptable for working with linear systems. Now, depending on the actual equations in the system and the way that they're presented to you, one method might be more appealing than another at any given time. So in this part, we're going to look at our first method, which is going to be a graphing method. So there really won't be anything new to learn here because we've already discussed the concept of graphing a linear function or a linear equation. So we did that back in section 6. If you need to pause, go back and review section 6. Now would be a good time to do so. So looking at my system, or at least example 8.2, it says, graph the given system in a Cartesian coordinate plane. Then we're going to use the graph of the system to solve the system. So let me go ahead and label the equations in my system, equation 1, equation 2. And I want to work specifically with equation 1 for a moment. Equation 1, 2x plus y is equal to 1, appears that it's going to be a linear equation, and it should be because that's what we're dealing with here with our systems, but let's verify. If we subtract 2x over, we would get y equals negative 2x plus 1. Which certainly gives us the mx plus b feel that we want out of all of our linear equations. So for this particular equation, m would be equal to negative 2 and b would be equal to positive 1. So that means the y-intercept is at 0, 1. Our slope is the ratio negative 2 over 1. So I can use that to find a second point, and I'm going to go ahead and get a third, fourth point. Go back to my y-intercept. Let me get a fifth and a sixth point. And I'm going to try to draw a straight line for this. So just as a heads up, when you're graphing as a method for solving a system, you need to have a great deal of precision when you do this. And I'm going to label this as the graph of equation 1. If you don't have a great deal of precision with this, then whatever you estimate as your solution won't end up working. And so you want to be as precise as you possibly can, so that way it takes as much of the guesswork out for what you think the solution is. Alright, equation number 2, we'll go there next. That is 3x plus 4y is equal to 14. So again, with the experience from section 6, this should be linear, but let's go ahead and verify by getting it into the mx plus b form. This will be 4y equals negative 3x plus 14, and then y will equal negative 3/4 x plus 7/2. So it does have the mx plus b format. M would be equal to negative 3/4, b is equal to 7/2, which is equivalent to the decimal 3.5. So let me come up here to the y-axis at 3.5. We'll mark that point, and then from that point I need to use the slope. Let me go down 3, to the right 4, and let me see if I can go up 3, 1, 2, 3. It takes me a little bit off the grid, but not too bad. That's going to put me about right there. And that's important to be able to help me to draw my straight line. Since I don't have a straight edge, it does present a bit of a challenge for me on that. Okay, there we go. And that would be the graph of equation 2. So that's the first part of the example. Graph the given system in the Cartesian coordinate plane. That's done. The second part says to use the graph of the system to solve the system. Well, this would be an intersecting lines case, which means we have one solution. There's one place where these 2 points intersect, and it looks like they intersect at the point -2, 5. So to verify this, I'm going to do what we did in section or example 8.1, where we would just take the ordered pair and plug it into the different equations. So this is going to be a check step. So we're going to check to see how does this ordered pair work with the different equations. So we're going to let x be equal to -2, y be equal to 5, and then equation number 1 is now going to say 2 times -2 plus 5 equals 1. So I'm going back to the original representation of the equation for my check. That's a good habit to get into, just in case you make a mistake with the rewriting of the equation for graphing. So this will help catch some of those kinds of errors if there are any. -4 plus 5 is supposed to equal 1, and it absolutely does. 1 does equal 1, so true statement there. Number 2, let's check out that one, or that equation. 3 times -2 plus 4 times 5 is supposed to equal 14. So that's -6 plus 20 is supposed to equal 14, and it does. 14 does equal 14, true statement. So therefore, our solution set is the ordered pair -2, 5. It is the only solution that we have, and that's what we'll box in.